Welcome learners. Let us now look into the natural response of RC circuits. This lecture is the continuation of the series that we are going to have on first order RL and RC circuits. In the previous lecture, we have learned how the natural response of RL circuits behave graphically and mathematically. In mathematical portion, we have seen the expressions for the voltages and current, and following the same guidelines of deriving the expressions for LC circuits, now we are going to look into the expression for the RC circuit or the natural response of an RC circuit. So in this topic, we are again going to look into the expressions for voltages and currents that arise due to release of energy in case of capacitor being the electric energy, or to put it more specific, electric charges. So when the capacitor loses energy in the form of charges, we are going to see what is the mathematical behavior of voltages and currents for the RC circuits. So to understand the natural response, we have already come to this understanding that whenever a sudden voltage source is removed from a circuit having a resistor and capacitor, we are left with a single capacitor connected to a single resistor, and thus we get the RC configuration. So we need to understand the behavior of this natural response of RC circuits in terms of voltage and current expressions. So in order to understand this, we begin again by a simple circuit, and this is the representation of the circuit where we have an independent voltage source connected with a resistor, and now we have a knife switch over here connected to a capacitor, and this is your capacitor C, and then we have its respective resistor connected to it. So this is point A and point B, and this is the switch that is available, which is going to be open at t is equal to 0, or the switch is going to switch at t is equal to 0 from point A into point B. So now these kind of switches are, as we talked earlier, are known as SPST switches, which means single pole, single throw. Single pole, single throw switch. They are specially designed to make the connection before breaking them, thus to avoid the condition of current reaching towards infinity in the generic equation for the inductor. So let us look into this circuit and see what analysis we can get. So initially the switch is at point A. So initially switch is at position A for a long time. This long time is a very important term, meaning when the time was less than 0, the switch was at position A. So long time means that the voltages or current sources have reached their steady state condition, or the maximum values have been attained by the circuit in terms of the voltage and current sources. So when the switch was at point A, the only circuit elements available to us were a voltage source with its resistor and a capacitor, if this being point A. So in this scenario, when a constant supply of voltage was provided to the circuit, all of the voltage appeared across C1. So we can say that our initial voltage V of 0, or initial voltage V of 0 was equal to Vc, and it is the same voltage which is appearing across the capacitor V of C. So this is basically V of C. So this is the initial condition that we had, and a constant voltage is now appearing across the capacitor, which means that when a constant voltage is appearing with the mathematical expression of capacitor in terms of current, the current becomes 0 ampere, and thus the capacitor is working in the open circuit condition. So this is basically what is happening when the switch was at position A. And we can say that the initial condition is V0 negative comes out to be Vg. And we know from our previous understanding of RL circuits that in order to avoid the abrupt change, we always make use of special kind of electronic switches such that the initial condition V negative or 0 negative equals to the final condition V0 plus, and for both these cases the value will come out to be the source voltage Vg. This is again done in order to avoid the sudden or abrupt change in time which will lead to an infinite current. Thus, in order to avoid this, we basically consider this condition for the this condition for the capacitor as we saw previously with the inductor. So now let us see what happens at time equals to 0. So at time equals to 0, the switch moves from A to B. Switch moves from position A to position B. When it moves to position B, our new circuit will just be a capacitor connected to its resistor. So now we have a capacitor and resistor, and the voltage appearing across will be Vg. And now since this configuration is received, so we say that now this is the natural behavior, or we call it as a natural response of RC circuits. So now we want to see that what is the natural response of this kind of a circuit in terms of the voltage and current expressions. So let us derive the expression for voltage and then similarly for the current, power and energy. So for voltage, we basically apply the node voltage method over here, where we select any node and we consider the flow of currents. Obviously in this right hand direction there is nothing, so we are moving towards the capacitor and resistor. So in case of capacitor and resistor, we can say that IC plus IR equals to 0, and the current in the capacitor is C dV by dt plus V by R equals to 0. Let us do some algebraic manipulation. I can say I will have dV by V equals to minus 1 by RC and minus 1 by RC, and I can get rid of this T over here by multiplying it with dt on both sides. So this and this cancels out. Now in order to, so my equation becomes dV by d is equal to minus 1 by RC multiplied by dt. In order to find the voltage, we need to integrate this whole term on both sides. So I'm going to represent V with X and T with Y just to make a generic integration. So if I integrate this as dx by x and I write it in terms of minus 1 by RC to dy, so I can write the limits as V naught of t initial value to V of t, and same goes from 0 to t. Once I integrate this, this becomes ln of x with limits from V naught of t to V of t, and this becomes 1 by RC, and this will be just t with its limits 0 to t. So again applying the logarithmic rule and putting in the values, I will get ln V of t minus V naught of t equals to 1 minus RC into t. If you put the limits, you will get just t. Solve the log, subtraction becomes a division, as we saw with V of t, V naught of t equals to 1 minus RC into 2. We multiply this by an exponential on both sides. So as per rule, the exponential and log cancels out, and this V of t goes to the opposite side. So I'll have V of t is equal to V naught of t is basically V0, because this is at 0 time instance, so we take it to be 0, and the exponential will now have a power of t divided by RC. And now we know that the initial condition V of 0 is equal to the positive sign, which is equal to Vg. So I can write my V of t is equal to V naught e raised to power minus t by RC, given t is greater than equal to 0. So this is the expression that I have for the voltage appearing for the RC circuit. You can consider this V0 or VG because this is the initial voltage that is appearing over here. So I have written over here. So this is the equation for the voltage or expression for the voltage. If we want to basically understand this voltage, so obviously we know if we plot this, this is a voltage or the form of electric energy in the form of voltage that is released by the capacitor. So initially it is going to be a voltage of V0 and then there is an exponential decay and then it reaches to its final condition over here. So this is exponential minus T by RC. Again here R and C are the decaying current because of the exponential, and this is where the R and C are controlling the decay of current, and eventually when T reaches infinity we get the steady state condition or the maximum value the capacitor can hold, and which is obviously 0 in this case because all of the energy, electric energy which is released by this capacitor is going to be utilized by this load resistor in the form of dissipating heat. Once all the charges have been accumulated, we reach the electrically neutral position, there are no extensive charges, then the resistor will become cooled down and thus all the energy will become equal to 0. Similarly, we can also get the equations for the current and the power, but the important thing is the time constant for RC circuits, and in this scenario we can see that this is the ratio. So time constant is 1 divided by RC, and which is basically the value. So the time constant comes out to be RC. This is tau. So here this is basically 1 divided by T by RC. So it becomes the time constant in seconds. So time constant is basically letting us know that how much time the RC circuit is going to take to reach its steady state condition. This is the same behavior we saw with inductors. So if you haven't seen that lecture, you can visit that lecture back. So steady state condition is also represented by the integral multiples of tau, and normally we know that when the system reaches 5 tau constant or time constant, we say that the system has reached its steady state condition. So for RC it is RC is the tau or the time constant. Similarly, equations for currents and voltages and power will be extracted from here. So I is equal to Vt by R. We all know what is V of t. So it is going to be V naught e raised to power minus t by RC divided by R. Again, this is for greater than and equal to 0 plus 0. Having a plus sign here means that we are only considering the condition when the switch has been changed from point A to point B. If the switch was at point A, then this condition is not going to be valid because the sudden jump will create an infinite current. Similarly, the power comes out to be V naught square by R e raised to power minus 2t by tau for t is greater than equal to 0 plus. And finally, energy for this RC circuit comes out to be half C V naught square 1 minus e raised to power minus 2t by tau for t greater than equal to 0 plus. So these are the equations for the current, power and energy of the system. Again, if you put the value of tau as infinity in the energy equation, so the initial energy for the capacitor will be half C V square, V naught square. So this is when t is less than equal to 0 and t equals to infinity, as we saw with inductors. So now let us look at an example and see how can we find the necessary or how we can analyze an RC circuit in terms of an example. So let us say we have this example question where we are given this circuit. So we have an independent voltage source connected to a resistor, then we have our switch, then we have the capacitor connected. So this is point A of the switch and this is point B. The capacitor is 0.5 microfarad, voltage is 100 Vg, resistor is 10K, and then we have another resistor another resistor in parallel to it, and then we have another parallel resistor. So this is the combination that we are having. This is a 60K resistor, this is 240K, this is 32K. What else do we have? We have the flow of current I naught in this direction. The voltage is V naught appearing across this 240 ohm resistor, and the switch is changed from point A to point B when time equals to 0. Voltage appearing across capacitor is V of C. So now in this we need to find these four unknowns. The first being find the capacitor voltage when time is greater than 0. Then we need to find the V naught T when time is greater than 0 plus. Then we need to find I naught T when time is greater than 0 plus, and finally we need to find the total energy, and that is across the 60K ohm resistor. So these are the four unknowns that we have to find. So let us solve this step by step, starting with the first solution. Obviously every solution related to the energy storage elements begins when the switch is closed for a longer time or the switch is at position A. So when the switch is at position A for long time, what is going to happen, or what is going to be the voltage? So when it is at switch A, the circuit that we are going to have will be a voltage source with a resistor and then a capacitor. So this is capacitor and this is the resistor and this is the 100-volt source. So we know when a switch is closed for a long time, or it is at position A for a long time, a constant voltage is going to appear across this, which means that the current is going to be 0 amps and the capacitor will act as an open circuit. So what is going to be the voltage appearing across this? So the voltage, or the initial voltage V negative, is going to be voltage at the capacitor, which is going to be 100 VG. So this is the initial voltage that is going to appear when the circuit is closed for a longer time. And we know that when the switch is moved from point A to point B, in order to avoid this abruption, a sudden abruption, we note that voltage V0 negative at point A is going to be the voltage at point B, and it is going to be V of G, which is going to be 100 volts. So this is the condition that we use to avoid the abrupt change, thus causing a current reaching to be infinite. So this is going to be the voltage that is going to appear. So now when the switch is at point B when time equals to 0, our circuit will be a capacitor followed by the combination of resistors over here. So this is our capacitor, this is 32K, this is 60K, this is 240K, and this is point B for the switch. And now we want to know what is the voltage. So we know the voltage over here is going to be VG, as we have seen from this condition. So our equation for VCT is equal to V naught e raised to power minus t by RC for t greater than equal to 0. So now we know that V naught is equal to 100 G. We need to find the time constant. So the time constant tau is basically RC. In order to find RC, let us simplify the circuit. We know the value of C, which is 0.5 microfarad, but we can simplify the resistor combination shown here. So this is basically resistors connected in parallel, and then they are connected with the 32 ohm. So we can find the R equivalent as 60 parallel to 240K, and then you plus it with 32K. So R equivalent comes out to be 80 ohm, and thus your tau, or time constant, comes out to be 80 multiplied by 0.5 microfarad, and time constant is 40 millisecond. So this is the time constant that we have for the first part. So now our base equation for voltage across the capacitor is going to be V naught e raised to power divided by RC, which is 100 e raised to power minus 25 t for t greater than equal to 0. So this is the solution to the first part, finding the variation of voltage inside the capacitor. Now let us go to the second part. In the second part, we have been asked to find V naught when time is greater than 0. So V naught is across this 240 ohm resistor. So what we can do is we can solve the circuit by, so this 60 and 240 are in parallel, so we can simplify this and then we can apply the voltage divider rule. Because our circuit is now a capacitor connected to a 32 ohm and this ohm, so this is 60k, this is 240k, and this is 32 with VC over here to be 100. So we can solve this very easily by finding the R equivalent, because the unknown voltage V naught is across this inductor. So what I can do is I can first find the R equivalent between 60 parallel to 240 k. This comes out to be 48 ohm. Now I can apply the voltage divider rule to find the voltage V out. So voltage divider rule, in order to find V out T, is I use VC, multiply it with 48, which is the R equivalent, and divided by 48 plus 32, and this comes out to be 60 e raised to power minus 25t for t greater than equal to 0. So this is the solution that I am getting for my circuit. So this is 25t for plus t equals to 0. So this is the V out that we are getting. So now let us move towards the third part of the question. So the third part says that find the current. So the current I naught is basically moving across this 60 ohm, and we already know what is the voltage appearing parallel to it. So we need to find the I naught over here. So it's simple Ohm's law. I naught T is equal to V naught by R. We already have V naught over here. So the answer comes out to be e raised to power minus 25 t milliamps for t is greater than equal to 0 plus. And finally, for the last part, we need to find the total energy that is available in the 60 kilo ohm. So power equals to I square R, and we know that this is I naught, we have already figured out from here, and R is 60k. So 60 kilo ohm multiplied by e raised to power minus 25t whole square. So this comes out to be 60 e raised to power minus 50t milliwatts. This is the power. Now in order to find the energy at 60 kilo ohm, I'm just going to integrate this P with d of t, and it should come out to be 1.2 millijoules. So that is the solution to this problem, which was related to the analysis of an RC circuit.